Hi everyone. Just about to do our second set of video notes today. The topic of today is going to be on something called a factorial and something called a permutation. They're both to do with the counting principles, but they're going to be new symbols and techniques we're going to use for solving these. Just a quick recap. Last class we talked about the fundamental counting principle. And the idea with the fundamental counting principle is that anytime that you want to figure out the way that two things could happen. So let's say that you're going to the pet store and you were going to bring home one cat and one dog, and that there were 3 cats and 4 dogs to choose from, and you want to know how many ways could I pick a dog and a cat. So I think I said there's 3 cats and 4 dogs. I might have gotten this backwards. Anyways, let's say you want to take 2 of them. You're making 2 choices, but you are doing a cat and a dog, not 2 cats, not 2 dogs. So you got a cat and a dog. You need to write down the number of options of cats, and there's 3 of them. And then you need to write down the number of options of dogs, and there's 4 of them. And to find the total number of combinations, you just multiply. So this would work out to 3 times 4 equals 12 possible ways. Now, you can do this using a tree diagram as well. You could have listed like number of selections. You could have branched it off into your 3 cats and then branched each one of those into 4 dogs. That's another way of doing it. The only other thing we talked about last class was about what to do if I ask the question or, if I bring a cat or a dog. And that's where you had to draw Venn diagrams for one outcome and Venn diagrams for the other outcome. And you had to add up all the things in here, all the things in here, and you subtracted what happened to be in the intersection of the 2. Anyways, moving on. Today's a different idea. So factorials and permutations. Last class we learned about the fundamental counting principle and when to use it. We are allowed to use it, so we can use it in and situations. So that's like picking up a dog and a cat. We can't use it in or situations, such as picking up a dog or a cat. And how many ways can a teacher seat 4 girls and 3 boys in a row of 7 seats if a boy must be seated at the end of each row? So let's unpack this question a little bit. 4 girls, so we've got 4 female, and 3 boys, so we've got 3 male. We've got a row of 7, so I'm going to write a blank for each person in the row. 1, 2, 3, 4, 5, 6, 7. And then we know that a boy must be seated on each end. Now, let's fill the ends in first. There's 3 options for boys, so there's 3 options for this first spot. Once we've picked one, that leaves us with only 2 options for the other end. And it doesn't matter which end you put the 3 and which end you put the 2, because you're multiplying them together and you'll get the same answer regardless. So now we've got to look at our inner 5 spots. There's no rules or restrictions about those. We can fit the 1 boy and the 5 girls in any, or 4 girls in any of those spots. But we've got 5 to pick from. So if we go left to right, 5 options for the first spot, 4 options for the second spot, 3 for the third, 2 for the fourth, or I guess 6th, 5th, and 1 for the 6th. If we multiply all of those together, we're going to end up with 720 possible ways. So you could rearrange the row every day for 2 years and still you won't run out of spots, or you won't reuse the same combination. So now let's look at the middle 5. The middle 5 people. So those were 5, 4, 3, 2, 1 right here. Could have been seated in 5 times 4 times 3 times 2 times 1, which is 120 different arrangements. This can be expressed as what's called 5 factorial, which is written with an exclamation mark. Now, this is actually a math symbol. This is a button that you're going to use on your calculator. What it means is it means to take all of the numbers below and multiply together. So like 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. So it's a shorthand way of writing a descending pattern of multiplication. The factorial function, n factorial, is defined to be the product of all positive integers up to and including n, i.e. n factorial equals n times n minus 1, which is just one number less than n, times n minus 2, times everything in between until you get to 2 times 1. So it's just a general way of writing any number factorial. We've got to define 0 factorial for this notation to work. So 0 factorial will be defined as 1. So 0 factorial equals 1. In terms of how to find the factorial button, if you go to your calculator, underneath the alpha, so the green button, there's something called a math button. Go to that. If you go over all the way to PRB and down to 4, there's an exclamation mark, and that will get you the factorial. So to get to it, hit math, over to the right to problem, or probability, and then down to 4 for the exclamation mark. All right, let's do a bit of algebra with these. So 5 factorial. 5 factorial will be 5 times 4 times 3 times 2 times 1, which is equal to 120. 117 factorial over 116 factorial. Now, you could punch this in your calculator, but I'm going to show you how to do it by hand so you don't have to use the factorial button. I'm going to expand the top one out. So we know 117 factorial is 117 times 116 times 115 times 114. We could write it also as 117 times 116 factorial, because 116 factorial includes everything below 116. And the reason why I did this is now I've got 116 factorial on the top as well as the bottom. I can cancel those out, and it's just equal to 117. I don't even need to use the button on the calculator. Let's try this idea, but we're going to try it with variables instead of actual numbers, and we're going to see what we're able to cancel out. Okay. Now, I've got an n on the top, an n minus 1 on the bottom, an n plus 1 on the top, and an n plus 2 on the bottom. And I'm going to try to expand these out as much as possible. I'm going to take n, and I'm going to expand it into n times n minus 1 factorial. I still have my n plus 1 factorial. So I do need to try and reduce this a little bit. Oh, sorry, I forgot to write my n plus 1 factorial. I need to reduce the bottom. So I'm going to leave my n minus 1 factorial because I can cancel it out on the top. But I'm going to write n plus 2 factorial as n plus 2 times n plus 1 factorial. So I'm actually going to highlight the things that I've changed. I have gone and changed n factorial into n times n minus 1 factorial. I've left n plus 1 alone. I've left n minus 1 alone, but I have gone and written n plus 2 factorial as n plus 2 times n plus 1 factorial. So now let's cancel out what we can. N minus 1 factorial is gone. N plus 1 factorial is gone. And what we're left with is an n on top over n plus 2 on the denominator. On your own, same sort of thing. 10 factorial is going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's going to equal a large number, 3,628,800. 13 factorial over 11 factorial. I'm going to expand the top out into 13 times 12 times 11 factorial over 11 factorial. This is simply going to boil down to 13 times 12, which equals 156. And then lastly, n factorial over n minus 2 factorial. We can expand n factorial out into n times n minus 1 times n minus 2 factorial. We could keep going to n minus 3 and n minus 4, but we already have n minus 2 factorial. N minus 2 factorial goes on the denominator, and we can cancel it. We'll be left with n times n minus 1. All right. So now that we're done sort of defining the factorial, let's move on to something called permutation. So a permutation is an arrangement of objects, and I'm being really loose with the definition here because it's not explicitly numbers, it's not explicitly letters, it can be anything. It's an arrangement of anything. But the restriction is that it has to be in a specific order. So for example, words are permutations. The word book, B-O-O-K, is only the word book if it's written in that order. If you change it into O-O-K-B, it's now ook-b. That's not the same word, so it's a different permutation of the letters. We will find that sometimes the order makes a difference, and sometimes the order doesn't make a difference, depending on what we're talking about. So when we're doing permutations, for example, let's think about permutations of the letter A, B, and C. Think of it as a series of choices being made for each one of those letters. So how many choices for the first letter? Can you use any of them? So there's 3. How many choices for the second letter? Well, we've used 1 up, we're left with 2 others. So we've got 2. And when we get to the third letter, there's only really 1 choice. It's whatever we haven't used already. So if we want to figure out the number of permutations of A, B, and C, well, we use the counting principle, fundamental counting principle. First letter has 3 options, second letter has 2 options, third letter has 1 option. That means I have 3 times 2 times 1, or 6 permutations. Example, how many permutations are there for the letters A, B, C, D, and E? So now this one's a little different because there's 5 letters, but it's the same process. Use the fundamental counting principle. We've got 5 letters. How many options for the first letter? Well, we've got 5 letters, so 5. We've picked 1, so now there's only 4 options for the second, 3 options for the third, 2 for the fourth, and 1 for the fifth. So technically, this equals 5 factorial, or 5 times 4 times 3 times 2 times 1. We would have 120 permutations of those 5 letters. All right, on your own. 6 children are lined up for a drink at the water fountain. How many permutations are there of these 6 children? By the way, when you're watching these at home, if you've got the notes in front of you, pause the video and try these on your own. But I don't, unfortunately, I don't really have the option of letting you work on them because these aren't live. But that's not maybe a thought for you, maybe something that you can try out. So we've got 6 children lined up for a drink at the water fountain. There's 6 spots in line. We could draw a diagram, I suppose, but I think you can imagine this scenario. There's 6 kids in line. And technically, we could swap them out, swap the order out. So there's 1, 2, 3, 4, 5, 6 choices, essentially. Who's first, who's second, who's third, who's fourth, who's fifth, and who's sixth. How many permutations of the 6 kids are there? Well, since there's no restrictions, we can use any of them for that first spot. So there's 6 options. We've got 5 left for the next spot, 4 for the next spot, and so on until we've used up every one of our choices. So there's 6 factorial ways to arrange these 6 kids, which is 720 permutations. What if you're not using all of the objects though? So what if you only want to make a 4-letter permutation, but you've got more than 4 letters? We've got A, B, C, D, E, F. So that's 6 letters. But we need to use 4. So we use the fundamental counting principle, write our 4 blanks. But this time, we're not going to use up all our options. For the first blank, we've got any of those letters to use, so we've got 6 options. For the second spot, we've got 5 options, 4 for the third, and 3 for the fourth. But we're never going to get down to the point where we only have 1 choice left. So 6 times 5 times 4 times 3 becomes the number of outcomes. And the number of outcomes will work out to 360 permutations. And now I should really point out with permutations, the order is what's important. So because the order matters, we have this many options. If the order did not matter and it was just how many different combinations of 4 letters can you make, you're going to find far fewer outcomes. But because the order matters, because the word BED, bed, is different from DEB, deb, well, then those are both 2 options. So that is 2 options instead of 1. Okay. There's 26 letters in the English alphabet. How many 5-letter permutations are there? Assume each letter can be used at most once. This is another important thing. We'll talk about what to do if you can't or if you can repeat the letters. But for now, once we've used one, it's off the table. So we've got 26 letters, and I'm going to start writing n equals 26, just to remind us how many we've got to choose from total. So if we've got 26 letters to choose from, and we're making 5-letter words, we draw 5 blanks, and we fill in our number of options for each blank. The first letter, we can use anything, so there's 26. The next letter, we can use 25, then 24, and 23, and 22. If we multiply all those together, we can make 7,893,600 possible permutations. That's a lot of words, and that's only 5-letter words, and that's only using each letter once. So lastly, it is important to take note of whether repetition is allowed. Because if you're allowed to repeat letters, that changes things, and you can't treat these the same as we already have been treating them. If not, we will have far fewer options. And that's something we will talk about in the coming days. So today we talked a little bit about, we reviewed what the fundamental counting principle was all about. We talked about when we can use it and when we can't use it, and some other options like tree diagrams or Venn diagrams. We then talked about what a factorial is and where to find it on your calculator. It's in the math menu. We did some algebra with factorials, and we used factorials and the fundamental counting principle to talk about a permutation. And a permutation is an ordered arrangement of something. We solved some problems with permutations, and we talked about what to do, or at least we talked about what to look for when solving these problems. And that's things like repetition or specific rules or things that you can or cannot do. So that's where I'm going to stop the notes today. I've got some problems for you to try. This time they're out of your textbook, not the workbook, so keep that in mind. Page 243 of the text, 3 to 5, 6, you only have to do A and E, not A2E, and then 7 and 8. Please, while you're doing your work, make sure you're checking your questions as you go and marking accordingly. So I think I'll stop the video here. Take care, everyone, and I will see you all tomorrow.